Welcome to our Organic Chemistry 1 exam review number 1. We're going to be focused on Lewis structures, relation of structure and function, resonance, acid-base properties of organic compounds, and a few other odds and ends, including structural representations and things like that. So I've gone ahead and shared the picture of the practice exam where I'm going to be working from. Although I do want to emphasize that if you have any questions from any source whatsoever that you'd like me to go over instead, I am more than happy to scrap my original plans and go over any questions that you have. I am fully prepared to answer whatever questions you have and help you with anything you want help with. Cool?
Yes.
All right. All right. So, and of course, if there's anything that you want me to go ahead and skip, that's fine as well. So,
Okay.
First of all, let's take a look at Lewis structures. It's a bit of a refresher for those of you, and you haven't really talked about Lewis structures other than these past few weeks, probably since Gen Chem 1. But basically, to draw a Lewis structure, the first thing we want to do is count the total number of valence electrons in the molecule. Now, in this particular case, and I'm going to zoom in, and you might not see this in the video recording, but if you're watching this later, and you can zoom in as well on your screen if you're here right now. So, how many valence electrons does hydrogen have?
1.
Yep, and since this molecule actually has 2 hydrogens, I'm going to say 2 times 1. And then how many valence electrons does nitrogen have?
5.
Yeah, and that's 2 nitrogens, so it'll be 2 times 5. So I'll go ahead and multiply that. 2 times 5 is 10, plus 2 is 12. I have 12 total valence electrons. What you then want to do is you want to draw what's known as a skeleton structure. And the way that a molecule is written typically, like when it says HNNH, the way that a molecule is written, it's written to show connectivity. In other words, and connectivity is an idea that you're going to actually need to be familiar with in organic chemistry. Connectivity means how the atoms are connected to one another, or specifically the order in which the atoms are connected. Okay. Sometimes molecules can have the same connectivity, but different spatial arrangements, in which case we call them stereoisomers. And we'll talk a little bit more about that later. But for this one, the skeleton structure, I'll just go ahead and draw H, which is connected to a nitrogen, which is connected to another nitrogen, which is connected to a hydrogen. Now, recognizing, of course, that every bond is a shared pair of electrons, how many electrons have I already used up in this Lewis structure?
6.
Yeah, I've used up 6. I'm going to subtract 6 from this, because I have 6 left. So then I'm going to place my remaining electrons in pairs on atoms that do not already have a full octet. So my remaining electrons in pairs on atoms that do not already have a full octet. Now hydrogen, of course, can only ever have 2 electrons around. It can never have more than that. So I'll place 2 electrons on nitrogen, and then I'll put 2 here, 2, 4, and here's 6. So then I look and see, okay, well, is there any atom that is deficient? Is there any atom that has less than 8 electrons around it?
Then nitrogen.
Nitrogen on the right? Now,
Yes.
of course, the bonded electrons, these ones count as 2 electrons for both this nitrogen and this nitrogen. And forgive me if I'm telling you things you already know. I know that some of this is a bit of a review for you. So since this nitrogen does not have enough electrons, I'm going to have to share from an adjacent atom. So atom next to it has to share by forming an additional bond. And so I'm going to draw an arrow showing the electrons are going to go from there to here, and we're going to get this new bond that forms in between the two nitrogens. The the lone pair is going to go away now, and now I have my Lewis structure, a proper Lewis structure where all of the atoms are satisfied. Does that make sense?
Yes.
Okay. Now, number two, this is where people really start to get tripped up. Resonance is a really messy business for a lot of students. It's something that's a little bit weird and a little bit different, especially when it comes to hybridization. So I actually have a special page that I made up. I'm actually going to go ahead and pull this up and toss it in the chat. It kind of gives a breakdown of how you can identify resonance and acidity. Essentially, resonance is the moving of electrons between pi bonds, or moving of electrons in pi orbitals. And so as a result, for resonance to really take place, you generally want the orbitals to be either sp2 or sp, although generally speaking, the resonance in organic chemistry, most important resonance only involves sp2 hybridization. There is some sp resonance, but we're not going to really deal with that too much. The first thing we want to do is identify the hybridization, because this is also a question that a lot of professors tend to ask in terms of resonance. They'll say, what is the hybridization of this atom? What is the hybridization of this atom? So looking at this little carbon here, the one that has the negative charge on it, what would you say that the hybridization of that is? Or do you remember how to determine hybridization?
It would be sp3, right?
And you would think that it would be sp3. So your instinct is correct. You look at around it, it looks like it has 4 electron domains around it. And because it has the lone pair and 3 bonding domains. And normally you would say, okay, yes, that's going to be sp3. But it turns out that when you have a lone pair of electrons that is adjacent to, next to an atom that is sp2 hybridized, then this atom is also going to be sp2 hybridized. So let me kind of point out what I mean by that. So if I look at this carbon right here, and I'll just mark it right there. That carbon has 3 electron domains, so that is sp2 hybridized. I'll just do sp2. Actually, I'm not going to do that because that's too big, and I need to make it smaller. So sp2. And then if I look at the other carbon, if I look at the one up here, I'm going to mark it in orange. That carbon also has 3 domains around it. That's going to also be sp2. So because those are sp2 hybridized, the carbon atom here with the negative charge and the lone pair is also going to be sp2. And the reason is because resonance allows that negative charge to delocalize, because it's also like, since it's next to 2 atoms that have open p orbitals, those electrons can freely move throughout those p orbitals. And there's other factors as well that which you'll learn about later in organic chemistry that would encourage this delocalization. But in general, delocalization is favored. So anytime you see an electron pair that is next to sp2 hybridized orbitals, it likely will also be sp2 hybridized, or at least one of them will be. Okay, so what happens here? What what happens is, and I'm going to show this, the movement of the electrons with a black arrow. What happens is these electrons can either go over here and form a double bond there, or they can go on the other side and form a double bond there. Now, if they go over here where I've directed my arrow, that's going to cause the double bond here to break and those electrons to go to the carbon. In general, when you're moving electrons around in resonance, and you're drawing resonance structures, you only want to move them one place forward, so to speak. So in other words, you can move a lone pair of electrons from the atom that it's on to a bond between atoms. So you can go atom to bond, or you can move like the double bonded electrons that I moved. You can move those from bond to atom, but you don't want to ever go from bond to bond or atom to atom. In other words, I'm not going to want to, so I'll give you an example. I'll draw it here. So let's say if I had this, I don't want to, and just for the purposes of similarity, I'll draw another double bond here. So I would never do this. I would never go like this. And then and then put those electrons, and then put those new electrons on the other atom. So I can't jump from my lone pair of electrons from one atom to the next atom. I can only go from atom to the bond in between, or I can go from bond to one of the atoms. Likewise, technically speaking, you can do what I'm about to show you, but it's not going to let you see all of the different resonance structures. So technically speaking, you can go bond to bond, but that's not what you want to do, because that's not going to allow you to see all the different resonance structures. So I would recommend against that as well. So whenever you're doing resonance, only move it one place, atom to bond or bond to atom. So let's not do either one of these, okay? Okay, so having, now I needed those two arrows. Like when I moved this lone pair of electrons to the bond here, there's then 5 bonds around that orange sp2 atom. So I had to kick those double bond, I had to break that double bond and send those electrons to this carbon over here, so that this carbon doesn't have 10 electrons around it, because you can't violate the octet rule. So then, this gives me my first resonance structure here. And so I have a lone pair of electrons here, and I still have my double bond down here. I have my double bond to oxygen here, and I now have a double bond here. And there's a negative charge on this carbon now. I'm going to label my carbons just like I had previously. Label my carbons orange and the blue. Oh, actually, whoops, I lied. The blue is down here. That's the oxygen one. And the red is here.
The one that you just drew, yellow, right?
Oh, yellow. Okay. I'm colorblind. I can't tell if that's yellow or green. I'm sorry. I have really weird color blindness. All right. Sorry.
You're okay.
Okay. So one of the things you'll notice is that when electrons move towards an atom, that it becomes more negative. When electrons move away from an atom, it becomes either less negative or more positive. So for example, this red carbon used to be negative, but electrons moved away from it. So now it's neutral. right?
Yes.
And then for the orange one, electrons moved towards it, but then electrons here also moved away from it. So there's no change. Some moved towards, some moved away, no change. On this carbon here, the yellow one, electrons moved towards it, but no electrons moved away from it. So as a result, this one went from being neutral to being negative. Does that make sense? Does that help?
Yes.
Okay, so now we're going to go ahead and continue our little round robin here. I'm going to actually make this one pink and color code the whole darn thing. Okay. I think that's pink anyway. So here we go. These electrons can then either move back here, but why would you want to move them back there? That would just kick these electrons back up to the red. So we're not going to do that. That would just give us the previous resonance structure. We need a total of 3 new resonance structures. So the other option is that we could go and continue to go clockwise around. Now I can only move from atom to bond now, but that's going to put too many electrons on the pink electron, so that means I'm going to have to break this double bond and go from bond to atom. And I'll make this gray. There we go. Now I got all our colors. Okay, so then we go to our next resonance structure. So the oxygen still has a double bond there. We now have a lone pair of electrons on the gray carbon. There's a double bond now between the yellow and the pink carbon, and still the double bond between the red and orange carbon. And this one now has a negative charge on it because electrons move towards the gray atom. So what's the next step in this, do you think?
The electrons are going to move towards, like, right on the side where the double bond is.
You mean towards the oxygen one?
Yes.
That's right, yeah. Now, technically speaking, those electrons could move back the other way, but that would just give you the previous one, right?
Yeah.
So that's not going to help us get a new resonance structure. And then, there we go. Okay, so we'll move these electrons from bond, or from atom to bond. And that blue carbon is then going to have too many electrons around it, so we're going to have to kick the double bond to the oxygen off. And now this oxygen from the very beginning has always had 2 lone pairs. And I want to emphasize that here because we're going to see that's actually just about to change. Those 2 lone pairs. But now it's going to have 3 around it. So we have one more resonance structure. I now have double bonds here, here, and here. But the bond to the oxygen is now a single bond. And the oxygen had electrons move towards it. So it has the negative charge now. And that's how resonance works. Now the interesting thing about this, and this is why, and now you can see why that original red carbon was sp2 to begin with, because you see in most of the resonance forms, in most of these resonance structures, it has a double bond. So if it's capable of resonating and forming a double bond, that means it's going to take that higher hybridization. So anytime you see something that looks sp3, but it has a lone pair, if it's next to sp2 hybridized atoms, it will also be sp2.
Can I ask something?
No, I'm just kidding. Yes, of course you can. Go ahead.
Okay. When you began drawing the resonance structure, I noticed you first went on the right.
Uh-huh.
But if I had done it by myself, I would have went to the left first. Does that matter?
Not particularly. So in other words, you would have formed the double bond between the red and the blue carbon
Yes,
and
and then
picked
I
the
would have
electron.
moved the double bond to the atom to give it 3 lone pairs.
Yeah. So to move the double bond to the oxygen to give it 3 lone pairs,
Yes.
and and that makes sense that you would do that. Like, I mean, admittedly, that would kind of almost be like my default as well. The reason that I didn't do that is because the reason I didn't do that is because that would kind of get you stuck in the sense that once if you had done that, and I'll show you what I mean, and you could have done that, you could have done that, and in fact, if you had done that, okay, so here you go. So you would have had this, right?
Yes.
Yeah. The only issue there is that while that would have worked, um, what would you do next? If you put these, if you move these electrons down back here, then that means this would end up having to go back on that carbon, right? And you'd end up with the same thing you had before. In that case, what you might have ended up doing is saying, okay, well, here's one, but then what if I go to the other side and then basically draw 2 arrows from the original structure to do that, to show that, so that you're not like repeating those steps. Now, of course, I'm going to also show you another thing because I do think this is valuable. You might also be tempted to say, well, what about if I just did something like, um, what about if I just did something like this? I'm actually going to show it with purple arrows and had those electrons go there. Could that happen? And I just like, okay, well, let's see what that would look like. That's moving from bond to atom, so they're pi bonds. Technically, it could happen. It's possible. But notice what happens if we do that. Here, this oxygen now has a negative charge still because the electrons didn't move towards or away from that. Electrons did move away from this carbon down here, so that which I'll actually draw blue, that blue carbon. So now that's positive, and I now have another lone pair, so that's negative. Okay. Now, what's the problem with this resonance structure?
There's only 2, right? And there should be 3?
To what?
2 resonance structures.
Well, no, I mean, strictly speaking, I could keep moving electrons around and I could get more
Oh.
resonance structures in this. But what's the problem with this one? Because notice the question number 2 says, draw 3 other reasonable resonance structures. What's the problem with this resonance structure?
Is it that it has 2 negative?
Yeah, it has 2 negatives and a positive. Generally speaking, with resonance structures, the most stable, the most important, the most reasonable resonance structures are going to be those that minimize formal charge. So those that have the fewest number of charges on your different atoms, those are going to be the most stable resonance structures. And most reasonable resonance structures. Generally speaking, if you can draw resonance structures that only have like one atom with a formal charge, like the ones that I have above, the 3 ones that only have just one negative charge on the molecule, you're going to want to draw those. Those are going to be the most reasonable resonance structures. Or in terms of formal chemistry language, organic chemistry language, we would refer to those as the most important resonance structures because those most accurately reflect the nature of the molecule. Because in truth, none of these resonance structures really actually exist. The actual resonance, or the actual, what this molecule actually is going to look like is probably something like this. Delocalized electrons throughout the middle of the molecule, and you would end up having a partial negative here, a partial negative here. And that's what that little cursive, like that delta, so that kind of looks like a musical note. A partial negative there and a partial negative there. And in truth, you would actually maybe have a small partial positive here. It would be pretty minor, but you might have a small partial positive here because of the electron withdrawing strength of the oxygen. But that's what the molecule would actually look like. Like there's going to be a kind of a free floating of electrons throughout the entire molecule. And so there's going to be a partial double bond. And basically in the pi orbitals, because the sigma bonds, the single bonds, are the result of hybrid orbitals, the orbitals that kind of look like that, and then you get orbital overlap. This is from Gen Chem, so the orbitals overlap, and you get single bonds. But the dashed lines is a result of resonance delocalization from these pi orbitals. So these pi orbitals, these peanut kind of shaped orbitals, are in a ring here, and essentially the electrons just circulate through those pi orbitals, and so they kind of delocalize throughout the entire molecule. So that's what the entire molecule actually looks like. None of these resonance structures, it's not like it switches from one to the other. It's kind of like the best analogy is kind of like paint. If I mix yellow paint and red paint together, the color of the paint is not going to be red and yellow alternatively. Like, in other words, if you paint your wall with it, it's not going to randomly switch from red to yellow and yellow to red rapidly. Instead, the paint is going to blend and it's going to become orange. So all of these resonance structures are like different colors of paint. The truth is the actual, so to speak, color of the molecule is going to be a blend of all the resonance structures. I know it's kind of a little bit confusing, but does that make sense?
I think.
Okay.
But yes, I understand why I shouldn't go the other way when drawing it.
And like I said, you're not wrong to go either direction. You're totally fine going either direction. The only thing is, if you go the direction of the oxygen, you're basically going to have to back up and go the other way then.
Okay, I know what you mean.
Yeah.
I would have to end up going the other way anyway, because I would end up getting stuck.
Yeah, it's kind of like if you had if you're driving a car in a one-way street or whatever, you kind of, and you might be able to kind of drive in the parking lot right next to the other store, but if you go the one way, you're going to have to go all the way around the block. I don't know. Maybe that's a bad analogy, but it kind of, I don't know.
Yeah, I understand.
Okay. Well, obviously we're not going to have time to go through every single question in the entire test, but is there any particular questions that you'd like me to go over that would make sense, or that you'd like me to make sense of for you?
Well, I guess one would be Chiral Centers.
I'm sorry, what was that?
Chiral centers?
Chiral centers. Okay, yeah, sure. No problem. You're already starting on chiral centers? That's interesting.
Yes. For this
Okay,
first exam, it's going to be like chapters 1 through 3, so we won't cover acids and bases in our first exam.
okay. Well, chiral centers are basically any molecule that has, and I'll go ahead and switch over to the whiteboard. Um, so anytime you have a carbon that's connected to four different groups, um, then that would be considered chiral, because three-dimensionally its mirror image is not going to be the same as itself. So essentially, if you try to draw this three-dimensionally, I have a carbon, and then you have a wedge coming this way. That means it's coming out of the page towards you, and dash going this way. So let's say this is, your A, your E, and your D, and your B. Its mirror image, those are not going to be the same. Those are actually going to be different molecules, because if you tried to rotate this molecule around, yeah. Well, of course, chirality is kind of like, when I say four different groups here, like what I was leaving out, when I say four different groups, if a carbon is connected to something, if it looks like this, okay, so this doesn't actually at first glance appear to be chiral, but in fact it is, because the four things connected to that carbon are different.
Yeah, I
So
noticed there's an ethyl and a propyl group, right? And a methyl.
exactly. So you got you got a two carbon group over here. So it doesn't just mean what's directly connected to it. It also means um, everything connected on that side. So the three carbon group is different from a two carbon group, which is different from a one carbon group, which is different from a hydrogen. Um, now, have you learned RS configuration, or do you not need to know that about that yet?
No, we need to know that as well. We need to know E and Z and also R and S.
Okay. So, with regards to R and S, what you need to do is you need to manipulate the molecule so that the lowest priority group is in the back. Okay. So if you're given a three-dimensional molecule, okay, have you learned about Fischer projections yet?
Yeah, we started it a little bit.
Okay. So with a Fischer, this is the most common way that they usually give you these molecules to represent um, three-dimensionally. A Fischer projection basically implies that the top and the bottom group are going away, okay? And the side groups are wedged. So if you have a low priority group like a hydrogen, the lowest priority group you want either on top or on bottom so that it's going away from you, okay? So the top
Okay.
and the bottom are dashed, they're going away from you, they're going into the page, and the side groups are coming out of the page towards you. So let's say I drew a Fischer projection for this molecule, and let's say I have like the hydrogen on top here, a CH3 here, a CH2, CH2, CH3 here. And then I have a CH3, CH2 here. If I wanted to figure out what is the orientation of this, is this an R or an S compound? What I'm going to go ahead and do is I'm going to determine the priority by looking at the first atom to which it's bonded. So the first atom to which it's bonded is the same in each of the bottom three cases, okay? It's a carbon, carbon, and a carbon, right? So then I look at the next atom bonded to that carbon. Well, there's two hydrogens and a carbon on the bottom, but the carbon is the highest weight one, so that's the one that has priority. For the carbon on the left, there's two hydrogens bonded to that carbon, but there's also the carbon on the left here, so that has priority. And on the one on the right, there's three hydrogens that it's bonded to. So that one is going to be the hydrogen's automatically the lowest priority. I'll give it a number 4. This one over here, the CH3, is going to have a number 3. That's going to be the second lowest priority because it has hydrogens there. So then since the other two are tied, so to speak, I have to go to the next carbon. So this was tied, so I had to go over here. Okay. And now these are tied, so what's this carbon bonded to? It's bonded to hydrogens. What's this carbon bonded to? It's bonded to hydrogens, but it's also bonded to another carbon. So I'm always gonna refer to the highest molecular weight atom that it's bonded to first. So if I compare that carbon on the propyl group on the bottom to the hydrogens on the group on the left, the propyl group wins. And so that's going to be my highest priority. And this one over here is going to be my second priority. So this whole thing is second highest priority. This whole thing is the first highest priority, or the highest priority. And then there's the third highest priority. And then there's the hydrogen, fourth. Now I always ignore the lowest priority one, in this case the hydrogen, because that's in the back. And I'm just going to draw a circular kind of a circular arrow, starting with the 1 and moving around to 2 and then 3. Now, if the arrow is moving in a clockwise direction, that is going to be R. So this is actually an R compound. If it was moving in a counterclockwise direction, then it would be S. So this one is R. Now that's only true if the lowest priority group is in the back. What about if we had something like this? All right, so this is basically 2-bromobutane. Okay. Well, in this case, I mean, do you have to redraw this? Do you have to move it around? Do you have to try to manipulate it so that the H is going back? Well, the truth is you don't. If the lowest priority group is not going backwards, you can actually draw the arrow and then flip it. If it looks like R, it's going to be S. If it looks like S, it's going to be R. So comparing these groups, the bromine, the methyl, and the ethyl, the bromine is obviously the highest priority group because it has the greatest molecular weight. Hydrogen's the lowest. Now, and as you probably could figure out, the ethyl is going to be number 2 and the methyl is going to be number 3, right? Does that make sense?
Yes.
So if I'm drawing my arrow to try to determine if it's R or S, once again, I'll start with the highest priority group. I'll go to 2 and then I'll go to 3 and I'll ignore 4. Now this looks like it would be counterclockwise. It looks like it would be S, but in fact, this is R. It looks like S, but because the lowest priority group is not in the back, in fact, the highest priority group is in the back, I have to flip it to R. So it looks like S but it's going to flip to R. So that's a nice little shortcut if you don't want to try to manipulate these molecules in your head.
I don't understand how it looks like S because I thought it was R anyway.
Well, okay, so you got to remember, you always draw the arrow from the highest priority group towards the lower, from the number 1 to the number 2 to the number 3. Can you see how the circular arrow from number 1 to 2 to 3 is counterclockwise?
No, because that's clockwise, right? Because you're going from 1 to 2.
Does the clock go like this? Is that how the hands
Yes,
on the clock is?
that's counterclockwise, right? Yes.
Yeah, so that's counterclockwise. So that's a S. But because the lowest priority group is not in the back, even though it looks S, it's actually R. Over here, this is going clockwise. But the lowest priority group is in the back because Fischer projections always have top and bottom going back. Since the lowest priority group is in the back, this looks like it's R, and it is R. Does that make sense?
Well, when I first looked at it, I saw the bromine, and which is 1, and then I went directly to the ethyl, which was 2. So I thought it was R already.
We have to go around in a circle. You can't go from bromine down this way because you'd pass through this one.
Oh, okay.
You can skip the lowest priority group. You skip the lowest priority group, but in other words, you have to. But after skipping the lowest priority group, you have to go in the direction from 1 to 2 to 3. I can't go 1, 3, 2. I can't go like this.
Okay.
Does that help?
Yes.
How are y'all with naming? Are you pretty good with naming these organic compounds? So that's definitely something you're going to be required to do.
I think I'm okay with naming.
Okay.
Do you mean like IUPAC naming?
Yeah,
Yeah,
IUPAC
we
naming.
need to work on that because if you need to, then I'm fine with that because I guess I could use more practice.
I think on IUPAC for naming.
Sorry, you sound just a little bit far away. What did you say?
I said I think I'm fine on IUPAC naming.
Okay. How about your easy stereoisomers?
We can work on that. But once again, why was this R again? Because was the H on it wasn't on a wedge, right? Or it was.
Exactly. So if the lowest priority group is in the back. So think of it like this. So I'm gonna go ahead and write it like this. So for the one on this side, the one on the right, lowest priority group is facing away from you into the page. Okay? And the other side, lowest priority group is not facing away into the page. Okay? So if the lowest priority group is facing away from you, then that means clockwise equals R. Counterclockwise is S. However, on the other side, that ends up being opposite. Um, so since the lowest priority group is, and actually let me go ahead and move that up here a little bit, and I'm actually going to move this little 3 here too, up here, the 2 up here. There we go. So if the lowest priority group is not facing away into the page, then basically that designation flips. If the lowest priority group is coming out or not facing away, then clockwise would be S. Generally speaking, professors will just say always make sure that the lowest priority group is facing away from you, and then R is going to be clockwise, S is going to be counterclockwise. One of the ways in which it always helps me to remember that is that if you're doing clockwise, sorry about that, stop my phone. If you're doing clockwise, at the top of the arch, at the 12, at the number 12, where a clock would be, which way is the arrow facing? It's facing to the right, right?
Yes.
So right stands for R. So at the top of the clock, it's facing it's R. It's facing to the right. Whereas counterclockwise, it's facing to the left. So that would be S. And that's just one way I think to remember it, but that's with the lowest priority group facing away from you or going back away.
Okay. I think I understand it now. Because the way you have this organized is like the lowest priority is facing towards me, so that's R, right? Wait, hold on.
And it's not necessarily facing towards you, it's just not facing away from you.
Okay.
Because if it's in the plane of the page, in other words, it's not coming in or out, then it's not necessarily certain it's going to be one or the other. You have to reorientate it. But let's say these two groups are going away and then the top and the bottom are coming out. If the hydrogen is facing towards you, then clockwise is S, counterclockwise is R. If the hydrogen's facing away from you, the lowest priority group is facing away from you, then clockwise is R, counterclockwise is S. But you do need to have the lowest priority group either facing towards you or away from you. So you do need to either orientate it facing towards you or away from you to get a clear idea of whether or not it's R or S.
Okay.
Do you want to do anything with regards to Newman projections or cyclohexane conformations? Did you do anything with that?
Can we actually
Hannah?
really quickly go over diastereomers?
Oh, yes. That confuses me as well.
Diastereomers?
Yes.
Yeah, diastereomers.
Sure. I'll go ahead and clear this. Is that okay if I clear this?
Yes.
Okay, so let's do let me do a quick flow chart for classification of isomers, because I think that this will kind of answer some of those questions. So this is classification of isomers. So there's several questions you can want to ask yourself to determine what type of isomer you have, if you have isomers at all. And the first question is, do the two molecules have the same number of each type of atom? So in other words, the same number of carbons, same number of hydrogens, same number of oxygens, same number of atoms of each type? If the answer is yes, then we have to ask ourselves another question. If the answer is no, then they're not isomers. Not isomers. If the answer is yes, then the next question we have to ask is, do the atoms, I talked about this before, do the atoms have the same connectivity? In other words, are they connected in the same way? Same atoms connected to same atoms. They're connected in the same way. So if the answer is yes, then we have another question. If the answer is, whoops, I want to draw, I like my nose in red. Red is kind of a good color for now.
Yeah, it's negative.
Well, I love tomatoes, so red's not very negative in my mind.
Oh yeah, that's positive.
But yeah, no. If the atoms have the same connectivity, if they don't have the same connectivity, but they do have the same number of atoms of each type, they're what are referred to as constitutional isomers. Wait, whoops, I misspelled that. Constitutional isomers. So same number of atoms of each type, but they're put together in different ways. So if they do have the same connectivity, then you have to ask yourself another question. And the next question you have to ask yourself is, are the molecules mirror images of one another? Okay, so are they mirror images of one another? So the first, do they have the same connectivity? And the second, are they mirror images of one another? So if the answer is yes here, we have another question. If it's no, then they're diastereomers. So
Okay, but if it's yes, then that means they're meso compounds, right?
no. So if the molecules are mirror images of one another, then the next question you have to ask is, are they superimposable? And if the answer is yes, they are superimposable, then they're meso compounds. Oh, well, they're meso, or they are or they're simply identical, which meso are identical, but there's a distinction between meso and identical compounds, which I'm going to explain in a second. If the answer is no, they're not superimposable, that means they're enantiomers. Okay. So enantiomers, and diastereomers have several different classes. So there's different classes of diastereomers. So diastereomers can be either like cis, trans, or E, Z isomers. This is basically isomers with a double bond. Or in the case of cyclohexane, if they're both up or they're both down or whatever, cis trans or easy stereoisomers. But they can also be they can also just have two or more chiral centers that but the compounds but the configurations are not opposite. When when a compound has two or more chiral centers and the configurations are opposite, they tend to be enantiomers or meso compounds. So, like for example, if you have a compound that's two isomers that have the same connectivity, in other words, they're connected, the same atoms are connected to the same atoms, but one is RS and the other one is SR, they have opposite configurations. So therefore, they are going to be enantiomers. They're going to be non-superimposable mirror images. If you have one of them that is RS and the other one is SS, those are, and actually I'll write that as an example. An RS and an SS compound. The conformations, the stereochemical configurations are not opposite to one another, so they're not mirror images. One of them is opposite, one of them is the same. So they're not identical because they have different stereochemical configurations, but they're not opposite, so they're not enantiomers. So they end up saying that they're diastereomers. Basically, any stereoisomers that have the same connectivity but are not enantiomers are called diastereomers. And they can either be cis-trans or easy isomers, like with the double bond, or they can be compounds that have chiral centers, but the chiral centers are not opposite to one another, so they're not enantiomers. So enantiomers have opposite stereochemical configurations. Opposite, actually I'll put that in parentheses, opposite stereochemical configurations. All right, so I'll actually draw a little line under that as well. Now, if they are superimposable, then they can be one of two things. They can either be, they are going to be the same compound. But they could also possibly be meso. So the difference between just being the same compound and being meso is that a meso compound is a compound where its mirror image is the same as itself. So just as give you a little definition down here. A meso compound is a compound with two or more stereochemical centers. Two or more stereochemical centers, or two or more, I'll call it chiral centers. Two or more chiral centers that has symmetry such that its mirror image is the same as itself. So a compound with two or more chiral centers that has symmetry such that the mirror image is the same as itself. If something is the same on both sides, if you put it in front of a mirror, the mirror image is going to look exactly the same as the original compound. If you have something that's different on the two sides, if the mirror image is going to look different than one. It's like if you put your left hand up to the mirror image is not the same thing. The mirror image looks like a right hand if you put your left hand up to the mirror. However, if you were to put a glass of milk or something and hold it up to the mirror, that glass of milk was going to look the same as it does, like it's going to look the same in the mirror as it does in reality. Does that make sense?
Yes.
I'm not sure if my mic cut out.
No, it makes sense.
Okay, cool. So that little flow chart can be helpful. I don't know if it's helpful helpful to you, but I hope it is.
It actually is. I was gonna say, could you give us some like practice examples?
Absolutely. Okay, here we go. Can you see it?
Yes.
This says identify the relationship in each of the following pairs. Do the drawings represent constitutional isomers or stereoisomers? Or are they just different ways of drawing the same compound? And if they are stereoisomers, are they enantiomers or diastereomers? So this is kind of exactly the type of question I think you were looking for, right?
Yes.
So let's take a look at the first one, A. If you're looking at that one, does that look like it is going to be one of the ways you can tell here, if you're trying to figure out if they are, if it's something that's clearly chiral, like this one is clearly chiral, the carbon is bonded to 4 different groups, you can just determine whether or not it's R or S for both of the molecules. And then once you see that it's R or S for both of the molecules, then you can say, okay, it's either the same compound or it's a different compound. So what would be the first one? Is that R or S for A? The one on the left?
Okay. I'm gonna say S.
Yeah, that's right. Very good. Now, what about the one on the right?
The right from this is still A, right?
Yep, still A.
Okay.
Is it R?
Yeah, I was
Yeah,
gonna
good
say
job. It's R. So the first one's S and the other one's R. So what are these? First of all, are they isomers? Do they have the same number of atoms of each type?
yes.
Yes. You always want to check that first because sometimes the two molecules, one will be R, the other will be S, but it's a trick question because they're slightly different. So one has an extra atom or something. Okay, so these are isomers, and they have the same connectivity. They're connected in the same way. So because one is R and the other is S, what would that make them?
Oh, diastereomers or something like that, right? How do
Well,
you pronounce that?
diastereomers.
Yes. Okay.
Well, remember, diastereomers are when they have chiral centers, two or more chiral centers, but don't have, or actually, diastereomers is when they're not mirror images of one another. One of the ways you can check and see if they're mirror images of one another is if they have opposite configurations.
Oh, I got mixed up. Okay.
Do these have opposite configurations?
Yes.
So they're mirror images of one another, and therefore, they are
Enantiomers?
enantiomers. They're non-superimposable mirror images. They are enantiomers. If they have opposite configurations, and there's no symmetry. There's no symmetry in this molecule. You can't cut it down the middle and the one half looks the same as the other, right?
Yes.
And in truth, it is impossible to have, if a molecule is truly chiral, and it has one chiral center, it's impossible to have symmetry. It's impossible to have symmetry. Because chiral, in its very nature, is asymmetric. If you have one chiral center, it's automatically not going to be symmetrical. All right, so let's look at the bottom one. Or let's look at the next one, B. The molecule on the left. So first of all, do these have the same number of atoms of each type?
Yes.
Mm-hmm. Are they connected in the same way?
Yes.
Yeah, they have the same. In other words, the same atoms are connected to the same atoms. There might be different arrangement, but the same atoms are connected to the same atoms. Okay. So are these chiral? Are they mirror images of one another? And I guess the question is, do they have a chiral center? Before
Yes.
and they do?
Because and why don't they? Because I was gonna say
That caused you to doubt yourself, shame on me. No, the group on top, the CH2OH, is identical to the group on bottom, the CH2OH. So if you have two groups that are attached to that carbon that are the same, then it's not chiral.
oh yeah, it's the symmetry, right?
Yes, exactly. Well, exactly. There is a line of symmetry there. If there's an internal line of symmetry in the molecule, that means it's going to be achiral.
Okay.
But also the fact is that you need a carbon that's bonded to 4 different groups, and that carbon is not bonded to 4 different groups. So if it has the same connectivity and it's not chiral, then that automatically means that it's going to be the same compound. So these are not isomers, they're simply the same compound.
Okay.
What makes it constitutional isomers?
Constitutional isomers means that they are connected. They're not connected in the same way. They don't have the same connectivity. So if they're not connected if the same atoms are not connected to the same atoms, then they're not. They're going to be but there's the same number of atoms, but they're not connected in the same way. It's going to be constitutional. So if you look at, for example, E, look at E. Look at where that OH is relative to the double bond. Okay. The OH is the OH in the compound for E. The OH in the compound on the left is 1 carbon away from the double bond in that cyclopentane or cyclopentene, right?
Yes.
Yeah.
The OH on the right is 2 carbons away from the double bond on either side. Okay. So are the atoms connected in the same places?
No.
No. So that molecule does not have the same connectivity. In many ways it looks very similar, but it does not have the same connectivity, and therefore it is a constitutional isomer. Does that make sense?
Yes.
I have a question about B again.
Yeah.
So, because at first I didn't think that it was symmetrical because the OH is on a different side than the H. Than the hydrogen. So, are we basing the symmetry on from top to bottom? Like the fact that it's the same?
No, that's a good question. That's a good question. Let me go ahead and I'm going to share a different thing. I did a screenshot and put this in Paint so I can draw on it for you. Uh, Basically, if I'm looking at the line of symmetry for this molecule, the line of symmetry is right here.
Okay.
It kind of goes right through the middle of the molecule. You can see the top of that line is the same as the bottom, right?
Mm-hmm.
And the same thing with this one. So it has an internal line of symmetry. Now to your other, but that's not necessarily actually the easiest way. I mean, the first thing you want to do here is actually to um, identify whether or not the carbon is chiral or not. So like for example, in the first, for 1A, for part A, there's 4 different groups, right? I have a methyl, a hydrogen, a bromine, and a ethyl. I have the same groups here, bromine, hydrogen, a methyl, and an ethyl. So there's 4 different groups. So that's chiral. But if I look at the other one, I have a CH2OH, CH2OH, an OH, and an H. Well, 2 of those groups are identical. So that's not chiral. And if it's not chiral but it has the same connectivity, then that's going to be achiral. So you can either look for an internal line of symmetry, or you can just look and see if the carbon atom is bonded to 4 other atoms, or 4 other groups, 4 different groups. And like for part C, um, there's actually 2 stereochemical centers. One is the double bond, and the other one is the chiral atom. You have a CH3 right there. You have a hydrogen, OH there. You have a hydrogen here, and then you have this group over here. Those are 4 unique groups. So a carbon needs to be bonded to 4 unique groups in order to be chiral. And in this case for C, it is bonded to 4 unique groups and has the same connectivity, but has a different spatial arrangement because the OH is wedged on the left and it's dashed on the right. So these end up being enantiomers. It's interesting because, and this is also one of those weird things, because if it has a double bond configuration, the double bond configuration has to be identical, but the chiral configuration has to be opposite for it to be an enantiomer. So this is both trans. It's both trans and well, the first one, the one on the left, is trans and 1, 2, 3, R. Trans and R for this one on the left, and on the right, this is trans and S. And because of that, they end up being enantiomers. As opposed to for D, the one on the left is trans and R. But the one on the right is cis and S. So because it's cis and S, trans and R and cis and S, these are actually not enantiomers. These would actually be classified as diastereomers. Because when you have both a chiral center and a double bond, you need the double bond configuration to be identical and the chiral center to be opposite in order for it to be a mirror image. So those two are slightly more complex examples. I don't think your professor is going to give you anything like that, but just in case.
Okay, so that makes sense. So when it's enantiomers, there's one change, but when it's diastereomers, it's two changes.
Yes and no. Sometimes sometimes you can have two stereo centers, and it can end up being enantiomers.
Okay.
An example of that might be in the compound down here. Let's check it out just to be certain. I'm going to actually move this off to the side. So if I am assigning priority down here, and I'm actually going to zoom this in just because I can. Yeah. Well, that's maybe a little bit too big. Okay. So if I'm assigning priority here, and I'm actually going to use fine brush, assigning priority here, my bromine's number 1. My lowest priority group is the hydrogen, so that's number 4. And this group down here, of course, is going to be number 3. Well, actually, whoops, I lied. That's going to be number 2, second highest priority because it's next to a bromine, whereas this is just a methyl group here. Okay? So if I ignore now if I'm, keep in mind the hydrogen is off to the side here, so that's actually technically a wedge, which means this is going to flip my understanding here. But basically, I go 1, 2, 3. It looks counterclockwise, which would be S, but because the hydrogen is out in front, this is going to be an R. So R stereochemical configuration for that one. Now on the bottom, I'm going to use a different color here. I'll use green, I guess. The bromine here for this stereochemical center, the bromine is number 1. Now the carbon attached to bromine is going to be a higher priority than the carbon attached to oxygen, because bromine is a higher molecular weight. So this is actually going to be higher priority up here, 2, and this down here is going to be a 3. Okay, and then of course this is 4, which I could ignore. Once again, this is wedged because it's going out to the side in a Fischer projection. So the bromine, number 1, 2, 3. This looks like it's counterclockwise, but because the hydrogen is coming out wedge, that's going to flip this to R as well. Counterclockwise is usually S, but hydrogen is out in front, so this is going to be R as well. Now if I look at the other one here, so let's look at the molecule over on the left here. And this is tricky because this is not a Fischer projection, this is a sawhorse projection. This is so your bromine's number 1. You have the carbon that is attached to a bromine, that's going to be number 2, versus a carbon that's attached to oxygen, which is going to be number 3. So this is like this. Now in this sawhorse projection, this bromine is actually going back away, and this hydrogen is going back away. Now because the hydrogen is back away, this doesn't need to flip, and this is actually going to be, even though it's off to the side, this isn't a Fischer projection. In a sawhorse projection like this, the group going down is actually wedged. The CO2H is actually in the plane, and the two groups going off to the side, those are actually going back and away. So those are going to be dashed. So anyway, this is R. This is clockwise. This is an R. And for the bottom one, this bromine is number 1. This is number 2. Um, oh, actually, I should use a different color. I'm sorry. This bromine's number 1. This up here is going to be number 2 because it's attached to the bromine. And then this is going to be a number 3. Now, in this case, this hydrogen is actually wedged, just like the bromine is wedged. Because in the sawhorse projection, that those groups that are up front, those are wedged. Because from the perspective of this front carbon, this is going back into the page. The blue carbon is going back into the page. So anyway, this is going to be 1, 2, 3. And so that looks counterclockwise. We're actually going to flip to clockwise because of the hydrogen being wedged. So this is R as well. So in this case, they're the same compound. These are actually identical compounds. Even though they look different, they're actually identical compounds.
Okay. And how many
But
chiral
if
centers
one
are
was,
there?
if one was RR and the other was SS, then they would be enantiomers. One was RR and the other was SS, they would be enantiomers. But if one was RR and the other one was SR, then they would be diastereomers. If they have opposite configurations, they're going to be enantiomers if they have 2 or more chiral centers. But if they have the same configuration, that means they're the same compound. But if they have different configurations that are not opposite, that's when they're diastereomers.
Like when you say different configurations, do you mean if like the hydrogens on the first compound was pointing towards, and then the hydrogens on the second one was pointing back?
What about that?
Like I'm confused as to why it's like identical compounds over enantiomers.
Ah, gotcha. Well, you saw how I assigned them as RR and RR, right?
Yeah.
Okay. Did that make sense?
Yeah, because of the chiral centers.
Uh, so, um, so maybe what help? So if they have the same configuration, actually, I'm going to shrink this down because it's a little bit big. So same configuration equals same compound. Okay. If they have opposite configuration, they are enantiomers.
Oh wait, would that count as if like one compound was SS and the other was RR?
Yes. So if one was SS, the other was RR, or if one was SR and the other one was RS.
Okay, that makes sense.
Any case in which their configurations are opposite, that's when they're going to be enantiomers. But then if they have different but not opposite configurations, that is when they're going to be, I'm going to actually just drag this over here. That's when they're going to be diastereomers. That's when they're going to be diastereomers. So same configuration, same compound, opposite configuration, enantiomers, different but not opposite configurations, diastereomers. Does that help?
Yes.
Okay. Well, time has kind of flown on us here. We've reached our 12:30 deadline and gone past it. But if you have if maybe one more question you'd like to ask, I'd be happy to indulge. Otherwise, if you think you've had enough chemistry for the day, we can call it a day.
I just have one more quick question.
Sure.
For this compound that we just did, there's 2 chiral centers, right?
Yes, there are.
Okay, because from what I understand now, the 4 groups that the carbon has, they all have to be different.
Exactly. To be
Okay,
chiral, yep.
okay, that makes sense now.
hmm
So that's why the other example that we did was not chiral, because there was symmetry up and down. It was the 2
Yeah,
groups. Yeah, okay.
exactly. So yeah, there's symmetry. The top group and the bottom group are the same.
Yeah, okay.
Cool.
Thank you.
Yeah, you're so welcome. And feel free to let me know if you have any other questions. Feel free to come into the Science Learning Center. We're happy to help you out. I mean, I'm there till 6:30, and my colleague, who's also really good at organic chemistry, is there till 8. So we can help you out anytime till 8 tonight. Did you say your exam is tomorrow or is it on Monday?
Monday.
Monday.
Oh, it is on Monday. Okay. Well, feel free to come by and see us anytime today, tomorrow, or Monday before your exam. We'll be happy to help you out with any questions you might have.
Thank you.
Okay. Thank you.
You're welcome. Thank you for coming.